Okay, so let's see. We got 3 more lectures to go, and we'll see how far we can go for the materials. And your lab number 5, don't worry, sorry, not don't worry, don't forget about it. It's actually lab number 5. You gotta make sure you study the abstract classes, the interfaces, and the deadline will be next week. Check the deadline, please, on the PDF. And if you got any question about the final lab, reach out because that's also covered in your exam. I will talk about your final exam a bit, maybe in the last 5 or 10 minutes today's class. You can also ask me questions. And then based on your questions, maybe I can also incorporate my answer into a PDF and I'm going to release the PDF today or tomorrow. So it'll be complete information for you. Right? So in the last 5 or 10 minutes today, I'll talk about exam. And I put out some learning resources for you about recursion. That's certainly going to be helpful for your exam. I will show to you. If you go to the lecture site and scroll all the way down to the final few lectures there about recursion. So you will see that we got a slides already, and there's a notes over here just to summarize all the examples that we're going to talk about recursion. We'll cover some of them today. We're going to cover more on Thursday. And as for the exercises, that's going to be very helpful for your exam. I'm going to base on my questions related to recursion on these exercises. So if you do them, you should be good for exam. Should be in a good position. Let me say that. So there is one lab that I gave back in 2022, also to 2030. We just didn't really have it this time. I just decided to have lab number 5 for you on also inheritance. But if you want to try it out, and also I got solution for you. Right, try it out first and then look at the solution. That's going to be useful. And also the coding bet, especially for part 1 over here, this will be the more elementary level of recursion problem. I'll say try them out first, as many as you can. And for those of you who really want to try more, you can also try part 2 here. That will be the more advanced version over here. So for your scheduled lab tomorrow, I cannot really make it to any demo in the morning, but maybe in the afternoon, I can maybe pick some problem from there and go over with you, right? So you can come by, and then in the afternoon session, we can go over some recursion problem, okay? And for the example that we're going to talk about in the lecture, I got all the source code for you already on the Java, all right? So you can also download them, try them out, and look at the debugger, and etc. Right, that's what I have for now for recursion. If I got more, I'll post it here, as usual. Okay, so that's about recursion, which is definitely important for your exam as well. And about the review session, so the polling is still going on until, I believe, Friday. So if you want to indicate your availability, feel free. Okay. Any questions about the course for me to clarify? And as I said, I'm going to talk about the exam at the end of today. So don't worry, I'll talk about it. Okay. So let's now do a quick recap and then move on to recursion. We're going to solve problems today, just for you to get a feel about how to solve problems recursively. And then you could dive into the exercises I just showed to you on the lecture site, right? So that'll be the best plan for you to move on. All right, so last time we basically finished off the discussion about inheritance. And this example over here basically talk about if you just try to make some method call, the argument over there might make the method call not compilable for the reason that we explained last time. So you can refer to the notes or the recording. But by doing some downward casting, we are able to make the compilation work. However, for some of them, or for 2 of them, you're going to get into class cast exception, also for the reason that we explained last time. And then for this one here, you don't even get compilation pass, because it's neither upward nor downward casting. Right? So when you review this example here, try to go with the direction I just showed to you, right? You really want to go over to see, number 1, compilation. Number 2, can you get by the compilation by doing some typecast? And number 3, even if the typecast compiles, can you run into class cast exception? Right? So these are always the question you want to ask yourself, okay? And we talk about something so-called polymorphic collection. The essence of it is like this. So in your Java class, you declare some variable here. Let's say students of type array of students. And the student class over here, somewhere in the inheritance hierarchy. As soon as you have this kind of setup, you know that you have a polymorphic collection at the runtime. So it goes this way. The static type for every element in the array will be of static type student, just as we declare that to be. Number one. Number two, dynamically, because we have some mutator like as students, where the parameter type over here is very generous. It's basically at the top of the hierarchy. That will allow any subclass or descendant classes to be added into the array at the runtime. So if you look at the runtime, you can see at index 0, index 1, they simply store objects of different dynamic types. So that's the polymorphic nature of the array. And for this example here, we also use the instance of operators to really check the dynamic type. So this will be a very important example to really understand. You might see some variance in the exam. All right. So when you do the review, just try to understand why we call that polymorphic, right? It's really important to get that message clear. And then we move on to talk about something called polymorphic return type. What does that really mean? It simply means the return type over here for some accessor. Again, the class over here as a return type also sits somewhere in the inheritance hierarchy. Dynamically, the return objects can be of dynamic type any class that's of descendant class of the return type here. All right, so you can go over the tracing that we did last time, and also I assigned to you guys some simple exercise to trace the rest of the code. What you really want to see is when you try to make the same method call, for example here, and also here, by passing different indices, it's going to return different objects because the collection there is polymorphic. That means at index 0 versus at index 1, the dynamic type might be different. And the way to check it would be using the instance of operator. And the dynamic binding is going to be ensure that if you got S over here calling the same get tuition method, because of dynamic binding, the dynamic type of S over here, and the S is the return value from this method call. And the S over here is the return value from this method call. That one there, also dynamic type can be different. So the different version of the get tuition may be called as well. Right? We talked about details as well last Thursday. So you really want to also make sure you review this one here. All right, so from last Thursday, it's really important to understand number one, polymorphic collection, and also polymorphic return type, right? So they're somehow related. And then we talk about the type checking rules, and we spoke about this particular example, right? You can also review the rest as well. And we talk about dynamic binding and the overridden methods, right? So the idea would be in this specific case, you got overridden version over here in the ancestor of the dynamic type over here, right? You can see the dynamic type here. You basically got two versions here, ancestor number 1 and ancestor number 2. You got two versions over here. Which one should you choose? You should choose the one defined in the closest ancestor. So that's the rule, right? Just remember that rule. It applies not just to equals method, for any method that's actually overridden in the ancestor path. All right, so that's about inheritance. Anything you want me to clarify about inheritance in general? Okay. Yeah, inheritance is a very important topic, so you really want to pay attention to it, since we also we didn't really get a chance to have a written test on that, so I'm definitely going to ask you a question about inheritance in the exam. So just make sure you go over all the slides, all the examples, and get yourself clear about each topic. All right, and then we move on to recursion. Okay, so let's now recap very quickly about how you solve a problem recursively in general. So there are two cases. You got base case, you got also recursive case. We'll see these two cases for every example that we're going to talk about today. In the base case, it can be more than one base cases, but the essence of it is the problem itself is a very small problem, which you have to answer right away. It's like you can return the result right away without doing any further computation. On the other hand, if your problem that's given is big enough that you don't really have an answer right away, in which case we call that a recursive case. What we should do is so-called divide and conquer. We divide the original problem into strictly smaller sub-problems over here. So this, and this individually are strictly smaller than the original problem. And then the most critical phase is we're going to assume we have solutions to each of the strictly smaller problems. So we got accordingly 1, 2, and 3 solutions. And then to really get the solution for the original big problem, we simply somehow combine these solutions together and get it. Right? That's something, the pattern I will keep repeating about a concrete problem that we're going to solve today. Right? But the principle here is really important. Maybe it still seems pretty abstract to you. I agree. It's pretty abstract. But let's understand the principle first. And then when we solve the recursion problem today, hopefully we can get through at least 2 or 3 problems today. And then you'll see exactly what I mean by base versus recursive case. Okay. And then, yeah, the call stack, that's something we spoke about already when we talk about exceptions. So for that part, I'm going to assume you guys are okay about the concept for call stack. And this was the first problem that we tried to solve last time. And let's do a quick review. Okay. You all know factorial. The non-recursive solution would be when n is equal to 0, defined to be 1. Otherwise, it's going to be n multiplied all the way down to 1. That's a very simple definition. However, as I explained on Thursday, this solution here is not recursive because in the solution itself, you don't see any reapplication of the same problem factorial. You don't really see that. All right. On the other hand, this solution over here that we sketched very quickly on Thursday, this will be called a recursive solution. Why? Think about n factorial here. That's the big problem we're trying to solve. We cannot solve it right away, maybe. So we say if the size of the problem here is simply just 1, we have the solution right away. Just return 0. That's base case. On the other hand, when n is larger than or equal to 1, that's what we consider is too big to solve right away. So what we do instead is we assume we actually got the solution to some strictly smaller problem. So n minus 1 factorial, you can see n minus 1 is strictly smaller than n. It's a strictly smaller problem. And then you can see we are again applying factorial. That's another problem, right? It's like a solution to the strictly smaller problem. And once we have got it, we're simply going to combine that with something else. Once we combine them together, we get a solution for the ultimate big problem. Okay, so somehow try to go back to the different phases that I spoke about earlier to see how they can fit in to this particular definition here. Of course, we don't see any Java code just yet, but we're going to see that very soon. All right, any questions so far from last Thursday? Okay, so let's see here. If no, I think the first job we should do is to look at the Java implementation for this factorial problem here. And then we're going to do some tracing, and then I'm going to show you 2 possible ways of doing tracing. One would be the higher level tracing, which I'm going to use for most of the problem. That's actually easier for you to think about the design of your recursive method. Another one, which you should also know, is by using the call stack. So deal will be, I'm going to do the factorial tracing using call stack on a simple example just for you to get an idea. There will be a challenging one to also use the call stack, which I'm going to assign as exercise to you. But I do have a video solution to that. So you should do the exercise and look at the solution if necessary. All right, so let's now take a look at factorial. All right, we're going to see how to turn this recursive solution design into Java. All right, we're going to see that. Okay. Just to remind you, this is the recursive solution here. And then this is a Java method. Of course, it might be rewritten in a different way. You can definitely explore. But let's stick with this particular version. Maybe the easiest one as a hello world example. So we're saying that we have some accessor that's going to return integer. And it's called factorial. You can see factorial somehow got called at least once by itself. So it's a recursive method, right? Remember how we identify recursion. Whenever a method itself is trying to call, whenever a method in its implementation is trying to call itself, it's a recursion. Okay. And we simply got some integer result, and then we got some if then else to reassign the result to something, and then we're going to return the result. Right? That's the overall picture. And we say when n is equal to 0, corresponding to the base case, we're going to assign the result to be 1. Right? That's exactly the base case. On the other hand, else means n should be larger than or equal to 1, or not equal to 0. In that way, we're going to say n here, multiplied by n minus 1 factorial. So we're calling the method here to calculate factorial of n minus 1. So you can think about when you are designing the solution for this method here, right? You gotta go for the following order. Number one, think about what might be the base cases. In this case, just 1. Right? When n is equal to 0, easy for me. I'm just gonna assign the result to be 1 right away. And then when I get to the else part, that would be the recursive case. What should I do? What I do is I assume I got factorial n minus 1 for me to use already. Simply write it out. You don't really need to worry about exactly how factorial n minus 1 is calculated. Somehow behind the scene, we're going to see how to do tracing of it. But when you design the recursive method, you can just use it right away. So this one here is assumed for you to use. All right. So this will be a very important factor over here for you to remember. This one here is somehow you assume and available for use. Okay. And then we just combine this assumed solution with something else. When I say something else, that simply means some extra computation that you might decide necessary for that particular problem. All right, any question about the Java code itself? Any question here? You should really be able to, number one, identify it's a recursion. Number two, you should really identify we got base case, we got recursive case, right? All right. Let's now see how it works at the runtime. And we're going to trace this particular input, number 3, factorial 3. Well, if you calculate in your mind, it's going to be 6. All right, but we're going to see exactly the 6 is going to be calculated. And I'm going to show you two possible ways of tracing. We'll get to the stack in just a moment. Let me show you the first approach, which I think will lead you further than just call stack. To some extent, call stack is too low level. It's a bit like just tracing exactly what a computer is going to do for you step by step. But when you design recursive solution, in some way, it's a very it's a creative arts for you to really design. So you don't really want to be too distracted by runtime stack. But you should know as well, right? Don't get me wrong. All right. Okay, so how would you trace that in a high level? So think about, you basically got factorial 3 to start with. All right, and then you look at the two cases. You got case number 1, you got case number 2, right? Only 2 cases. Case number 1 apparently is not applicable, right? So factorial 3 does not have the immediate result right away. So what we should do instead is going to be, we're going to do this one instead. All right, so think about, we're going to branch out to 2 things. We're going to say it's going to be boiled down into 3 times factorial number 2. Are we okay with this critical step? I want to calculate factorial 3, and I'll fall into this else case. That one there is going to calculate 3, which is n, multiplied by factorial n minus 1, which would be 3 minus 1, 2. This tells me that in order to calculate this, I need to recur on this one here again. And now the question is this already a base case for me? No, because base case requires a size of 0. So this one here, further down, is going to be, according to it, 2 times factorial 1. All right, so theoretically, we can keep going deep until we reach the base case. That's the critical thing. And then, is this the base case yet? Not really, because 1 is not equal to 0. So we're going to go further, and branch out is going to be 1 multiplied by factorial 0, right? It's going to be n minus 1, which would be 0. And now we know pretty well, factorial 0 over here has reached the base case because it's reaching 0. You can see the way it works is you have to keep going deeper for the recursion until you reach the base case. That's around the time you can start terminating the execution. All right. If your recursive solution is such that you will just go deeper, deeper, and deeper without ever return back, then you got trouble. You got stack overflow, something so-called. All right, good. Let me do a little bit annotation here so I can see the correspondence. let me see. This is a one instance of the problem, and this is another instance here, and this is another instance, and this is another instance, right? You can see, to solve this one here, we're gonna solve something strictly smaller. To solve this one here, you gotta solve something strictly smaller. To solve this one here, you also gotta solve something strictly smaller. And this one here is small enough, all right? That's kind of the flow. So what's gonna happen? So let's say, talk about this guy here. This is the base case. That means we're gonna get 1 as a result. So this one here is gonna be returned by, replaced by 1, like a returning 1. And how do we calculate this guy here, given that this one here that we depends on already returned? According to definition, 1 times 1, which will be 1. So that means this one here can also return with 1. How do we calculate the next one, which will be factorial 2? 2 times 1, which will be 2. All right. How do we calculate the final original problem here? 3 times 2. That's going to be 6. So 6 will be the ultimate answer for us. So this is what I call the higher level tracing. And this is something I'll stick to more for the subsequent problems. But I think I definitely should really do one example together with you to see how the cost that will work. And then I'll assign you some exercise to try. All right, guys. Any question about this tracing so far? Hopefully that's not too bad, right? It's intuitive, right? Okay. Okay, let's now go a little bit ugly. Let's see exactly how this will work at a runtime. It's not too bad. But as I trace, you can see things can go very, very lost if you somehow were not careful enough. Okay? But this one is not too bad. Okay, let's give it a try. So let's say I want to execute factorial 3. So what I will do is I'm going to push factorial 3 onto the stack. And this one here corresponds to this one here. You can think about when we do the high level, we're going to go top down. When we go call stack, we go bottom up. A little bit like that. Okay. And then how do we trace factorial 3? Let's go into the code. So n here will just be 3. And then because the base case does not match, so we're going to go to the else part. By definition, it's going to be 3 times factorial 3 minus 1, which will be 2. Agree? Okay. And factorial number 2 is going to be pushed onto the stack. So currently the execution for factorial 3 will be suspended. Right? So we're going to finish this one first. And this one here, let me highlight it over here. Factorial 2. So factorial 2. And that one there, you can see now correspond to this one here, right? 3 times and 3 times, all right? How do we calculate factorial 2? Well, similar. We're going to execute the same block of code over here. So now n will be 2. We don't really match the base case, and we're still matching the else part. So by definition, it's going to be 2 times factorial 2 minus 1, which will be 1. All right. And then for factorial 1, let me also show you the correspondence. Let me show better. Factorial 1 over here. And I can now push that onto the stack, which will be factorial 1 over here. Okay, factorial 1. You can see now we are down to factorial 1 here, here. That one there is going to be multiplied by 2, as we said here, to calculate factorial 2. Right? Don't lose the track. We're almost there. And how do we calculate factorial 1? It's still not a base case just yet. So we're going to have 1 here as the n, the input, and it's still not a base case. So we go to the else part. By definition, it's going to be 1 multiplied by factorial 0. All right. And this one here, let me see, green. Not that green, actually. This green. There we go. All right. And I'm going to push that onto the stack as well. Factorial 0. There we go. All right. You can see now we got factorial 0 here. Now we're reaching the base case. Let's see exactly how things should be finished, which is also important. Gradually, we're going to finish the execution for each one of them one by one in the last in, first out order, right? We talked about the stack structure earlier. We're going to calculate this one here, pop it off, calculate this one, pop it off, and etc. The ultimate answer we'll get is from this calculation, the ultimate answer, right? Let's see this one here. When we execute factorial 0, now we got 0 over here, and now this time it does match the base case. And that one there is going to calculate the result being equal to 1. All right. And that one there is simply just going to return, and you can replace it by 1. That tells you that it's going to return 1. What will be the next method to really execute? According to the stack, after this guy return, pop it off the stack, we should calculate factorial 1. Right? How do we calculate that? According to the calculation, it should be 1 times factorial 0. Right? That's from the earlier suspension. Right? You can also check the recording later. So to calculate that, we're going to do this. All right? So this part over here is going to be the result for factorial 1, which will be 1 times factorial 0 from earlier calculation should be 1. Right? So we got 1 times 1, just 1. So that one there is going to be just 1. So when you pop it off the stack, it's going to be 1. All right, so far so good. Let's finish that. And then we get to the next method, which would be factorial 2. By definition, it's going to be 2 times factorial 1, right, from the previous suspension. And that one there, we know that factorial 1 has returned back to us already 1. So now to calculate factorial 2 is going to be 2 times 1, which will be 2. That means replace this one here by 2. All right, returning 2, basically. Final step. The final method to really execute, that's the only thing that's left on the stack, factorial 3. By definition, it will be 3 times factorial 2, which we just got, which is good. So this one here is already, we know that it's 2, and then we're going to calculate over here. So 3 times 2 is going to be 6, right? Replace this one and return 6. So we get the same result. Oh, let me use the, how about yellow? Okay, I think given that our time in the class is so precious, I only want to do one, tracing the stack. But as you can see, even for simple example like factorial 3, it's not that trivial to do this. Agree? So that means, in general, you don't really have to go down to tracing using stack in general. To really design the very creative recursive method, try approach 1. That's something I'll try to convince you when we do more example today. Right? It's really this guy here that's going to lead you much further. Also in 2101 as well. All right? All right, guys, any question? Yes, please. Yeah. Mm-hmm. Mm-hmm. Yeah, exactly. So you can think about it in this way. Whenever you say return result, you know the result here can either be from the base case or it can be from the recursive case, right? Yeah. Hmm? Either, yes. Because we got if else, right? So you can think about once we declare the result locally, it will be reassigned either by the if branch or the else branch. So once it's reassigned, we're going to return the result. You can think about exactly where the result is going to be stored. It's not up to us. It's up to the Java runtime, which they have some way to really keep track. So the way for you to maybe keep track will be every time when you take out the method call from the stack, you can simply put what's the return result right away. So you will keep track for yourself. Yeah, I think a Java runtime will do something very similar, just very low level. It's not worth our time tracing that one too. Yeah. All right, guys, any other question? Yeah, for those of you who might be taking 2101 with me again in the winter, hopefully we don't need to go over this Hello World once more, right? It's pretty straightforward. We can focus on something that's more difficult. All right, anyway. Let's now do another problem here, and then I'll assign you some very useful exercise to do, okay? And I'll also give you a solution, of course. All right, the next one here, Oh, sorry, before the next one. Let's look at common errors first. So take a look at this particular factorial, like alternative factorial implementation in Java. This one here has a problem. Can anybody spot it right away? No base case, all right? You can see here, the good thing is when it tries to call the recursive, make a recursive call, it does try to make the problem strictly smaller from n to n minus 1. That's a good thing. But the problem is if you don't really have a base case, what's going to happen is like this. Let's trace now by the call stack by using the approach number 1. If I do factorial 3, in turn, it's going to calculate, for example, 3 times factorial 2, and then in turn, it's going to calculate 2 times factorial 1, and in turn, it's going to calculate 1 times factorial 0. This is where we should really reach the base case. But according to a code block over here, it's not going to do that. What it will do is it's going to go further indefinitely. For example, here, 0 times factorial minus 1, and keep going indefinitely. So that's a problem. You're going to run into something called call stack exception, something like that. Right? So you can definitely give a try on Eclipse, and you'll see how you can reach that call stack infinite recursion. It's a very typical error. All right, another common error is kind of the opposite. You can see here, I do have an base case, which guarantee I can definitely reach the base case if I have to. But what's wrong with it? It kind of violates another principle that we talk about recursion, right? Of course, you need to have base case, but you got to make sure. Yes, go ahead. This will also, I agree, will also be Stack Overflow, but for a different reason. You're basically not reducing the problem to be solved on the recursion. Yeah. So this one here is basically equally bad. So give a try here. If I try factorial 3, by definition, we're going to reach the recursive case 3 times factorial 3, and then it's going to be 3 times factorial 3, and so on. Also infinite recursion. All right, that's another error you want to avoid. These are very basic errors, but you'll be amazed. We sometimes might run into these errors quite often, right? Got to be careful, right? Always have a base case, and always when you want to make a recursive call, the input size must be strictly smaller. Okay? Any question about error number 1 and error number 2? All right, very good. Okay, let's now problem number 2 for today. And let's have you guys seen this before? Fibonacci number. All right. For those of you who haven't, there is a pattern over here, right? So we got 1, 1 to start with. Every time you want to calculate a number starting from the third position, it's always going to be the sum of the previous 2 numbers. For example, if you look at 21, it's equal to a plus 13. If you look at 89, it's equal to 34 plus 55. Right? Similarly, 21 is equal to a plus 13. Right? It's a so-called Fibonacci sequence. In 2101, we'll actually look at exactly the running time for like an efficiency for calculating this. But for 2030, we don't need to worry. But we need to have a working solution for calculating the Fibonacci number. All right, so here you can see 1, 1 here. 1, 1 is what we call the base case. And we call that F0 and F1. So F here stands for the Fibonacci sequence. And when you put a subscript 0 and 1, that means number 0 and number 1. Index. Think about indices goes like 0, 1, 2, 3. You know, actually, I should really say 1 and 2. That'll be less confusing. Sometimes people like to start with 0. But I think for this one, let's be consistent with the slides. 1 here and 2 here. All right, so you got indices, position, 1, 2, 3, 4, and etc. And then, for example, if you look at this one over here, this one here is basically F. Okay, let's see, 1, 2, 3, 4, 5, 6, 7, 8. That one there is exactly equal to the sum of the previous 2. So it would be F6 plus F7. All right, that's a pattern. For those of you who have seen that, you know what I mean. If you haven't, maybe try to look at the pattern more and try to convince yourself. Okay. Before we come up with the recursive definition for Fibonacci sequence, right? Let's think about what if I want to calculate, for example, Fibonacci 4. Okay, think about it. All right. If I want to calculate Fibonacci 4, it's basically here. 1, 2, 3, 4. Here, right? But let's not look at the sequence just yet. Look at this one here. So the size of the problem is 4. This is certainly not one of the base cases, right? It's not. We only know that we can immediately tell you F1 is 1, F2 is 2. Sorry, F1 is 1 and F2 is 1. That's something I can tell you right away. Anything that goes beyond the first two positions is considered too hard to tell right away. All right, so now in order to calculate this, we can solve a strictly smaller problem. But this particular problem here tells you can solve two problems at one go. Okay, so what's going to happen is to really calculate this one here is going to be F2 plus F3. Hey guys, one final time. Okay, so here we got F2 plus F3. Right? You can see in order to calculate F4 is going to be the sum of the two previous numbers. Okay, and now we can calculate them individually because F2 is considered too big to solve, and F3 is also considered as too big to solve. And to solve this one here is going to be actually, this one isn't that a base case already, right? So this one I know. This is already the base case, which is just 1. All right. And then how do I calculate, for example, F3? By definition, it's going to be F1 plus F2. And now individually, they're also base cases. So F1 here and F2 here, they're also base cases. So 1 and 1. So if you calculate these two, 1 plus 1 is going to give you 2. You can see the 2 corresponding to F3 over here. And then you got F2 over here. That one is also 2. So it's also 1. And then how do we calculate F4? 1 plus 2, which is going to be 3, which corresponds to this one here. Right? So that's how it will work at a high level for recursion. Quick recap, and then I'll tell you what you should do as exercise. So here we got F4 here. That's what we want to calculate. Recursively, we need to calculate F2 and F3 separately and combine the result using plus. And this one here, luckily, is already the base case. So we can return the result right away. And F3 here will be F1 plus F2. You know, similarly, right? That's good. All right, let's now take a quick look at the Java code, and then I'll give you the exercise to do. So this is a recursive definition, which I just mentioned, right? You got F1, F2, and also anything that's bigger, starting from F3. The Java code is not too much away from the mathematical definition, right? If you look at that here, so we have Fibonacci number is actually making a recursive call twice, over here and over here. So that's a recursive method. Again, we have some result. And eventually, we want to return the result. When it is equal to 1, when it is equal to, the result will just be 1. So these are the two base cases. And the recursive case is going to be some recursive call on n minus 1. N minus 1 is strictly smaller than n. Also, plus another recursive call result, n minus 2, which is also strictly smaller than n. So we got two recursive calls. That's something you want to identify right away. It is not uncommon to really have more than one recursive calls. So we have two recursive calls. And then somehow we try to combine their result together. And that's going to make the solution to the original big problem for size n. Right? Again, we correspond to the principles I went over in the beginning today. Okay, any question about the Java code? Okay. If you try to trace, for example, Fibonacci 4 is going to look very similar to this one here. So that one you don't need to do. That one I already did it together with you. That one will be the high-level tracing. But for the call stack, it will be required for you to know how to trace this particular Fibonacci number here. So what you need to do is to trace the execution for Fibonacci 4. So what you should do to start with will be put Fibonacci 4 over here and then go on until everything returns and see the result. All right, that's a required exercise. You know, I may put some similar question on the exam, so please make sure you do it. It's good for your understanding. And I'm gonna also put some video solution for you to go over as well. But let's not do that in the class. It's gonna take too much time. Okay. It might look simple on the high level, but it turns out to be quite tricky to get right. That's why you really want to try this exercise. Okay, any question here about this second problem here? We're good? All right. Okay, so I would suggest we do a little bit of Java code over here, and that will nicely introduce to the problems I want to go over, and then we'll take a short break. Okay. Okay, so I think the first set of problems on recursion that I would like to talk you through will be on the string. And let's go over some string methods, just make sure you understand how the string methods work. Okay? So we have a class called string tester, right? Which have some main method. You can make a JUnit tester if you want to. But let's now go over some method, especially we want to see how the substring will work. And also there's another method called character add. Okay, so these are the two methods, especially for substring. For those of you who never use it, it's a little bit tricky. So I want to get it right. And for the recursive problem that we're going to talk about after the break, they all depend on substring. So that's why it's important. And if you think about a string, for example, let's understand the string as a character array. So if I say I got a string over here points to, let's say, hello. The way you can visualize it is it's pointing to an array of certain size. How many characters we have? Let's see. 1, 2, 3, 4, 5. Okay. So 1, 2, 3, 4. So indices 0, 1, 2, 3, and 4. And index 0 is going to be H, E, L, L, O. So you want to understand that when you try to use a character add method here, the I you put over here should be starting from 0 until the length of the string minus 1, like an array. So there is another method you can also use called s.length. And notice that it's a method call, so you got to put the parentheses over here. All right? All right, so that's about the basics for the string. And understand the string as an array. And let's now go over the substring over here. All right? The formal definition for substring goes like this. When you say s.substring, you can pass some index I and some index j. Okay, I and j. I and j are simply integers. All right. What it will do is it's going to find the characters in a particular range, not exactly from I to j inclusively, not really. That's why it's a bit tricky. So it's going to get all the characters from this particular interval, I and then j. Have you guys seen this in the math class before? Right? This is like a closed interval. That means I should be included. On the other hand, j here should be excluded. So it will be as if. You basically say I and then j minus 1. All right? So this is something you have to remember. Otherwise, things wouldn't work for you. Okay? Let's look at some example here. So if I say 0, 0, that's a tricky bit, right? If I say 0, 0 here, it will be as if I say 0 and then minus 1. I want to get all the characters from 0 to minus 1. This is a special case where the I here is larger than j. So this will just give you an empty string. So whenever you specify the I and j over here, where the I is simply larger than j, that means empty string. It's a base case usually. Okay, substring. Sometimes you might find it useful. Okay, again, if you put, for example, 0, 0 here, it will be as if you want to get from 0 to -1. So this will be the rare case, what, like a base case, where 0 is larger than -1. Typically, it should be the other way around for the relation. In this case, it will just give you empty string. All right, so this will give you empty string. What about when you say substring, let's say 0 to 4? This will be as if you actually got from 0 to 3 inclusively. So that's why it's going to give you, so the string we are talking about is A, B, C, D, right? So think about indices are 0, 1, 2, 3. So if I say 0, 4, it's going to go from 0 to 3 inclusively. It's going to be A, B, C, D, right? That's the result. On the other hand, if you got 1, 3, what would that be? You go from 1 all the way to 2 inclusively, right? So that would be 1 and 2, which will be BC, right? And etc. That's about the substring. Okay, I'm going to put down some property over here for you to think about, okay? About a substring, which should really make sense. So let's say for any given string, S, okay? It points to some string object, let's say. Let's say we are given 2 integers. Sorry, just one. Given I, integer I, such that, let's say I is a valid index for character at. So 0 less than or equal to I less than or equal to s dot length minus 1. Okay, so we have I here, we have s over here. How can I use the substring method, taking I as the input, and reconstruct s? I want to say s dot equals. And then I'm going to put some long expression over here. Okay. And I want the equals to return true. And I'm going to put some concatenation between 2 expressions over here. And then I'm going to say s dot substring. Something here. S dot substring. All right, I'm going to give you the answer right away, but you can think about why it works. The first character should be 0. The last character, okay, let me put the comma here. The last character includes, well, it should be excluded. So this here should be s dot length. Not s dot length minus 1, right? And then I can simply put I here and I here. All right, think about why this will work. You can simply find some example string and check it out. All right, so that's the property. You want to be convinced. All right, this will always return true. And try some example yourself and make sure. Okay. Any question about the string method here? We're good? All right. All right, why don't we take a short break, and then by taking attendance, and then I will talk about the recursive method on the string after the break. All right, so before the break, I think we were now up to this particular slide. Let's take a look. So that's a slide about the call stack. You can just review the background. That's the same as when we back to the exceptions lecture. All right, let's now take a look. So that's a Fibonacci, that's a factorial problem we solved. And then we got to the common errors. And then we got to the Fibonacci number example here. Yeah, you can feel free to try a different way of programming. That's definitely fine. If you, for example, just don't want the result to be here to be reassigned, just return, that's also fine. Okay. All right. So that's the detail tracing textually, but you can also try the visual one, which I assigned to you as exercise. Okay, and that's the string code fragment that we went over before the break. All right, let's now try to solve different problems. They're pretty straightforward, but definitely give you some insight about recursion. I got 3 here. Hopefully we can get through each one of them today. All right, the first one is called palindrome problem. Okay, for those of you who don't know what a palindrome is, it's basically a word that's going to read the same forwards and backwards. All right, it's a very typical recursive problem that can be solved nicely. Of course, you can use a loop if you need. Okay, so our goal is to write a method that's going to going to return true or false, whether the word is a palindrome or not. Okay, let's now take a look at some example here. Now, is empty string a palindrome? Should be. It read the same, but forward and backward, it's just empty string. What about a single character string? It should be. I agree. That's good. What about madam? The same, huh? Okay. You can try as well. It reads the same. What about race car? The same, right? Okay. What about man? No. Okay. Good. That's a palindrome. All right. So now we want to see how we can solve this problem here recursively. Okay. And to really solve this problem recursively, let me change here. I think it's more, well, once we get to the Java code, it's very obvious about how it should work. But it's more important to see the insights about designing the solution, right? So let's talk about palindrome. If I were to design this problem here, I want to think about, for example, here, this race car over here is a string that's too long for me to get an answer right away, whether that should be a palindrome. So what I should think about is, how can I somehow make that into maybe different parts so that some strictly smaller part can be used or can be assumed to have the solution already. That's about a recursion, right? I want to somehow break the string down into strictly smaller string or strings so that I can make a recursive call on that. All right? And for this one here, I can just tell you right away, the trick here is, in order to be a palindrome, because you're going to read forward and backward the same. So when you read forward, you're going to see this character the first. When you read backwards, you're going to see this character the first. So if I can tell the first and last characters are already the same, I say it has a chance to be a palindrome. It may or may not be, but at least I don't really need to reject it right away. On the other hand, I got this particular string. The first character and the last character are already different. There's no way, no chance it can be a palindrome. So I can reject it right away. So that means in order for you to judge whether it's a palindrome, you can basically go from outside into inside of the string. So on the outside, you just need to look at the first character and the first and the last character. If they happen to be the same, you can somehow get rid of them and try to look at a strictly smaller substring. And that'll be the problem to recur on. On the other hand, if I see the first and last characters are already different, there's no need for me to waste any resources to compute any further. All right, that's the insight. When you do the exercise and when you just talk about it more general. Whenever you want to design a recursive solution, always think about some example and think about how you can make the problem just strictly smaller. Because for strictly smaller problem, you can always assume there will be a solution for that. You can use that solution to kind of combine together to make up the final solution. All right. So we're going to look at the first and last character, and the pink part is the substring that we actually want to recur on. All right. So we can think about this part over here is a strictly smaller problem. For us to solve. On the other hand, you can see this one here, A and also S over here, they're already different, right? You can see these two, they are not the same. That means no need to recur further. All right, any question about the inside here? All right, so that's about palindrome problem. And then if you look at the Java code, let's now go over a little bit and we can do one tracing together, okay? And for this one here, is palindrome here takes a string and then returns a Boolean, which makes sense, either true or false. And these are the base cases, which I say either or, right? The vertical bar. If the word is simply empty string reads forward and backward the same. Also, single character string reads forward and backward the same. So in these two cases, just return true. The else part over here is going to correspond to exactly what I said over here. We take the first character here, takes the last character here, and then we do a case analysis. If these two characters are the same, then we try to recur further. If these two characters are not the same, we know that we should return false right away. All right? So take a look. So you can see first character, last character using the char add, right? So make sure you're convinced about how to pass the input here, right? That's something we spoke about before the break. And the middle part, basically it's going to be the same string, strictly smaller, truncated the first and last character. That's why we go from index 1, the second character, and convince yourself why this is the case. All right? This is basically, it's going to substring here. It's going to give you the string with the first and last character removed. Right? Make sure you're convinced about this. But with the knowledge that I gave to you before the break about substring, you should be able to figure out. And when we return, if the first and second character are the same, and remember short circuit evaluation, right? If they are the same, that means it's true. And that means we're going to go ahead and evaluate further. On the other hand, if this part here is already false, then short circuit evaluation is going to make sure we don't go any further. All right? Of course, you can use if then else if you wish, but I'm just showing you some more efficient way of writing things. Okay, that's about palindrome. All right, any question here, please, about the coding itself? We can do one tracing very quickly. How about race car? So let's say we got is palindrome. And then here I got a race car. Let me write better. Okay, over here. So this will boil down into first character R, second character R. R equals R, ampersand, and then we're going to recur on the sub-problem over here. Is palindrome, and then ACECA. Are we okay with the first step? Okay. And this one here is not yet an easy problem for me to solve right away. Either a single character or empty string will work. So we're going to go further. For this one here, we're going to go further here. So first character will be A and A. A equals A. And then we're going to get is palindrome over here. And that will be CEC. Okay? So we're going to get CEC. And as you can see, so far it's simply just true. So we have to go on. Right? Okay, almost done. And then for this one here, we're going to get down to C and C. C equals C. And then all we got left would be just E. Is palindrome, and then just E. And indeed, you can see E here has the length 1. So we're going to return true. So this one here is going to be true. And I simply forgot to put ampersand at each level. All right, but you can see my point. So now we got C equals C, true and true, which will be true. And then A equals A, true and true, also true. And also R equals R, also true. And true, that's also true. So all the way to just true. All right. So the answer will be just true. That's a quick tracing about what's happening here. All right. And if you want to try some exercise, how about this one here? This palindrome over here. Okay, try that string and trace it. All right, that's your exercise. Okay. All right, let's now take a look at the second problem, which I think is more fun. All right, let's now at least do the second one. We'll see how much time will be left. All right, the second problem here is about calculating the reversal of a string. I'm pretty sure you may have seen this in the first year using a loop, but in the recursion, it's like very interesting to see exactly how that works. Well, let's understand what a problem is. Okay, if I got a string here, A, B, C, D, if I want, it's going to return another string that represents its reversal. So, for example, if I got A, B, C, D here, I should really get D, C, B, A. Basically, read it backwards. All right? That's the input and output. And let's get a little bit more feel to see more example. Okay, palindrome. Okay, reversal. Okay. So what will be the reversal for empty string? Just empty string, right? Nothing to write, empty. That looks like the base case. What about a single character string? Just itself, right? So now you can see in the two examples that we talk about, typically the base cases for strings or even array will be some substring or subarray of size either 0 or 1. That's typically the case, all right? And what about AB? BA, ABC, CBA, ABCD, DCBA, right? I think you guys are pretty okay with the base cases, but the recursive case is really the challenging part, all right? Let's now talk about it. All right. So you already know how it works. I'm going to erase this part over here. It's difficult, I understand, if you're only learning recursion, right? So I'm going to guide you a little bit. The way to really break through conceptually is to really see how can I break this problem here into some strictly smaller problem. The way we did it in the palindrome example there is to say, okay, I need to really get to this middle string here by first comparing first and last character, right? And now for the reversal, I could have done something similar. Maybe I'll try to get A and D and then somehow get a reversal and try to append A and D somewhere. That would be one way to go. But I'm going to give you some visual hints, okay? And then you can think about. That's a visual hint for you. Looks like the pink part is a strictly smaller problem. Looks like. And I'm not really trying to get the first and last characters. I'm only trying to get the first character only. That can be easier. So my visual hint tells you the following. If I can somehow get a first character there, and then for the remaining of the string, I will try to consider that as a strictly smaller problem. For sure, because it's one character less. But for the remaining part, how am I supposed to work on that? Right? For example, let's say this. What's the problem? I want to calculate the reversal of A. I want to calculate the reversal of, I'll say REV, of ABCD. Now I'm suggesting, if I can tell you that I know what the reversal is for BCD, and then I also know a way to really extract A. How can I now try to combine these two over here and make it a solution to the original problem ABCD? That's kind of my thinking process. Okay. Anybody? Robert? How do you concatenate? You mean concatenate A to reverse of BCD or? Okay, let's see. because it's a reverse, so A that used to be the first cannot be the first anymore, right? So what I would do is, why don't I try to reverse it to over here and try to concatenate them. Think about what's happening here. This BCD over here is a subproblem. And I assume that there will be a solution for it, like a reversal. And this one here, we know that conceptually it's going to be DCB. So if I can somehow get this solution here, DCB, and also get my first character and concatenate them together, I got DCBA. So that will give me the original, the solution to the original problem. All right? Think about it. Okay? And I'm going to go over the Java code with you, but let me see. I can give you another exercise to try. Okay? Another one for you to think about. Okay? The visual hints I gave to you looks like this, right? Another one, exercise. What if I give you the following visual hints? D here. This represents another possible solution to solve the reversal problem recursively. Right? Think about this one here. So this one here, I'm basically extracting just the last character here, and then the remaining one here will be the strictly smaller problem. All right, so this will be your exercise to think about. All right, but on the slides, it's basically this particular solution. All right, let's take a look. Okay. Okay, reverse off is the method name, and somehow we're gonna make the recursive call only once. Right? If it is empty when its length is 1, base case, just the string itself. Right? Empty string and also the string itself. So we got base case 1 and 2. And then what we do is we got something called a tail. Tail is basically this part over here. All right? Except for the first character. So you're going to start from 1. All right? You can see the substring here. And then we're going to make a recursive call on the tail and save the result into this one here. And then we're going to also extract the first character as the head, and then we're going to do this concatenation. And this part here corresponds to this one here. All right, so that's the Java method. All right, of course, you got to make sure you understand, number one, how to use a substring, and also how to really say, I assume this one here, so I simply just put it here, and catch is the return value. And then try to combine them together in a way that makes logical sense. All right? Any question here? Let's do some tracing very quickly, some smaller one. And then I can talk about the exam, okay? So I will leave some enough time. So let's say I call this R. How about that? I want to calculate the reverse of, let's say, A, B, C, and D. What it's going to do is it's going to have the first character here, A, and then the remaining one will be B, C, D. By definition, it's actually going to do A concatenated with the reverse of B, C, D. All right? That's the first step. Oh, beg pardon, should be swap. All right, just don't forget, you should always swap. Sorry about that. This will be this one here, plus. All right, good. So you can see what used to be the first character is now the last character at the end. And then what about this one here? So you're going to identify B here, and then CD, the remaining part here. So by definition, it's going to be B is now going to be put at the end. And then it's going to be the reverse of CD. Right? You can see CD here and CD here. And for this one here, you're going to identify, let's say, C here. And then the remaining part will just be D. Right? So that one there is going to be, again, C here, put at the end, plus the reverse of D. Okay? The reverse of D is matching the base case over here. So this part here is going to be You got exactly DCBA. All right. All right. Any question about this reversal? Yeah, we only talk about 2 string problems today about recursion, but do study these 2 and make sure the intuition is clear to you. We'll do another one on the string on Thursday to start with, and then we're going to move on to how to do recursion on the array. That'll be the example I plan to do. If we have time, I can do another challenging one maybe next Tuesday. We'll see how the time goes. But just remember, you are expected to really do lots of practice outside the class as well. That's the best way to really get recursion understood. All right, any question about what I covered today? All right, if no, let's now talk a little bit about the exam. Okay. Yeah, you know the time, and then also the venue. So the format there is going to be paper and pen. Most likely, you will be given a question booklet. You'll also be given some answer booklet. So you're going to put all your answers on the answer booklet. But you got to return both booklet back when you're done. All right? Just to make it clear. But I'll make it clear on the instruction. There will be mostly written question for you. There will be maybe some multiple choice. I don't want to commit to about how many. I haven't really finalized the exam yet. But mostly written, right? Let's elaborate this a little bit. Okay, you definitely have to do some explanation. You may have to do some output of the tracing. You may have to do some justification. Yeah, for example, if you recall in your written test number 2, you were given options about different G-unit and console tester. So I kind of ask you about which one should be valid, which one should not be valid. I might just give you one option and explain to me whether or not it's valid or not. Right? I'm going to need some justification. Right? Things like that. You might also be asked to write some code, but not to the extent that you're required to write in the programming test. Maybe you're asked to program a recursive method, most likely the case. I can tell you 100% you'll be given a question like this. Okay, you'll be asked to program recursive method, and I might give you a code fragment and blank out a few lines and ask you to fill out the blank. That's also possible. All right. That's about the coding. But you can ask me more questions. And the coverage, simple, just everything we have covered in the course. All right. Look at the lecture materials, look at the labs. And for the labs, you don't really have to redo the lab. I wouldn't recommend, since the final is happening not a coming Sunday, next Sunday, actually. So for the labs, I would suggest go over whatever solution you have been through for the labs, and then maybe take a look at the critical methods to understand how those are done. Right? I might blank out certain lines and ask you to fill it in. All right, and then slides, iPad notes. The way I design my exam question usually goes like this. I will go through the bullet point in the slides, and also I'll go over what I said in the class, and then I'll try to make questions from there. So everything you will see on the exam is something I have already covered. So that's a good thing. The bad thing is you got to make sure you review everything. All right. And coding bad, especially recursion 1. No data sheets, and sketch paper I will include it as part of the question booklet, so you can definitely have it, no problem. If you need more booklet, we'll also have the extra for you to use. And please make sure you bring your physical photo ID and also water snack. That's not a problem. Okay, any question you want to ask me about the exam, I can answer. We have some time. Go ahead. Yeah, guys, please, let's answer some question about exam. You may want to know. Yes, go ahead. Yes, I'm going to post an example question for you guys by the end of Friday. Okay, you're going to get some. And then I will confirm the time and location for review session as well. Most likely Zoom. I'll confirm the time with you. Yeah, go ahead. Yeah, so because it's going to be a paper and pen exam, so we're definitely going to give some partial marks, especially for coding. If you just start with some basic syntax, it's not too serious, we can definitely give you partial marks. Yeah. Mm-hmm. Good. So there could be a code tracing question about recursion. So it could be both ways. It could be either call stack, which I'm going to give you the video solution about the exercise. You can definitely make sure you do it. There can also be the high-level tracing, which I showed today. I'm going to show even more on Thursday. I'll be very explicit about what you should do. Yeah. Yeah, an exam is 3 hours. So I would say just get ready for it and go over everything. And then you still got time to ask me questions. All right, thank you. I'll see you on Thursday.